Okay, let's get started. Chapter 7, Quantum Theory of Atom. So, Quantum Theory of Atom, in this chapter we'll be learning electromagnetic spectrum. We'll be learning lot of new vocabulary, frequency, oscillation, wavelength. We'll be learning details about spectrum. And also, at the last part of the chapter, we'll be learning quantum numbers. Remember quantum numbers? There are 4 types of quantum numbers. We'll be talking in details to locate, to understand the details about the electron in an atom. Okay? So let's start with the first wave. What is wave? How can you make a wave? Can you see a wave? You don't see a wave, right? What is a wave then? What is it?
Repeating change.
Repeating change of a media, right? So it's a way of transferring energy, way of transferring radiation. Like for instance, sound wave. Sound make a wave to transfer the energy. Our sunlight have electromagnetic radiation. That radiations come to the earth through the media by disturbing the media by oscillation. So this continuous propagation of energy or radiation is called the wave. So that makes it, or you can say oscillation. So for instance, this media when disturbed, it goes like that. So this is just how the wave look like, and so continuous oscillation, and so the distance. So in the wave, we need to know a couple of terms. The terms are, first of all, wavelength, then frequency. So frequency, we use the Greek letter lambda. So lambda means frequency. And the wavelength is the distance between two waves. So for instance, this is the wave, this is the another wave. So distance between any two waves is going to be the wavelength. So this is the wave. So wave to wave, tip to tip, or valley to valley, or any distance to any similar distance. Distance between two similar part of the wave is called the wavelength. So this is also wavelength. And then, how many waves per unit time is forming? That's going to be the frequency. So frequency is how many waves is forming per unit time. That's going to be the frequency. And frequency and wavelength is like that. Look at that. This is the wavelength, higher wavelength than the other one. So if you draw in here, for instance, I can draw like that, you see? If you draw like that, what happens? If you see the distance between two tips, which is wavelength, so the wavelength, this wavelength is much bigger than the other one. That means this wavelength, we can decrease it here. But if you see, the wave formation is increases. So more waves is forming per unit time. So look at that. If you see the picture, you see it was 2 Hertz, 4 Hertz. But wavelength was higher than the other one. That means wavelength is decreasing, frequency is increasing. Which shows that based on the definition, and as you see, if you do the measurement, you will see that wavelength is inversely proportional to the frequency. this lambda means frequency, and this nu is frequency, and wavelength is lambda. They are inversely proportional. So the constant value, you can use this constant value instead of proportional sign to be C over nu. This C is a speed of light. Speed of light. So speed of light is distance traveled by light per unit time. So this is a very famous equation we use to calculate frequency or wavelength as needed.
And the speed
And
of light is constant?
It's going to be constant. So constant for what? Constant for any sort of light. For instance, this spectrum, right? In this spectrum, different radiation have different wavelength. Different radiation have, you see the top one is frequency, bottom one is wavelength. Frequency decreasing, wavelength increasing, you see? For each particular radiation. But for any radiation, disregard of what the wavelength is, their speed going to be same. The speed of light is going to be same. But why? How come they have different frequency, but speed they are going to be same? You can get this answer in here. If you see wavelength increasing, frequency is decreasing. Wavelength increasing, frequency is decreasing, right? So that means one decreasing, other one is increasing. So it's a beauty of mathematical equation. So C must be constant. In practically, it is constant too.
And that's the 3 point times 10.
It is going to be the 3.00 times 10 to 8 meter per second. So which is means 300 million meter per second. So what is this spectrum talking about? Do you have any idea about that? As I always go with a practical example in chemistry terms, I like to show you how it relates in our life, right? The first one is gamma ray, very high frequent. So high frequency means this is highly energetic. Energy and frequency is directly proportional. So high frequent means highly energetic. Have you heard the word gamma ray before? What is the gamma ray? It is a radiation, yes, but it is very strong. Have you heard in the world history never happened gamma ray explosion? Atom bomb. In 1945, right? Atom bomb was dropped to where? Japan. In Japan. So in Japan, Hiroshima and Nagasaki, right? 2 atom bombs was dropped. Do you know their names of the atom bombs?
I forgot. It's been a while.
One is Fat Man. Other one is Little Boy.
Yeah.
So Little Boy and Fat Man, 2 bombs were dropped. And you know what happened? Millions of people was died right away. Some was burned, some was died another destruction. Some people was still alive after the bomb, but they end up died because their DNA was affected by gamma ray. It's so highly energetic, it kills people by killing DNA. First of all, it burned everything, right? Very highly energetic, high temperature. I remember, I forgot the exact number, few thousand degrees centigrade temperature. Centigrade. It formed right there. The bomb was formed. Nowadays, Russia is saying that they have a bomb, they can destroy a country by single bomb. But Hiroshima was destroyed by one bomb, right? Not the whole Japan. Now Russia claiming they have a bomb, they can destroy a country with a single bomb. Anyway, world,
Good time.
we do not want that in the human history again. Do we? But what the North Korea thinking?
Little man got big balls.
Right, you're right. And they want to throw bomb anytime. I don't know what's going on, but they keep saying that. You know that, right?
Yeah.
He keep wanting to destroy, export his bomb. He already tested couple of times. It's not that only he's saying that, he proved it. He proved it by throwing bomb over the Japan,
Yeah.
2 months ago. So he showed his range of his bomb and missile, how far he could throw, And he easily claiming that he can pass Pacific to come in our land, here. Anyway, if they do that, that would be suiciding themselves, right?
Yeah.
Because they cannot destroy United States. It's a huge. US have power, all over the world, right? So they can maybe destroy part of the US if they want to, if they really want.
I don't think they could.
I don't think so.
Yeah.
It's kind of suiciding, But I'm scared though, by the way. When they read the news and then the way this young guy, president, right? Young man, the way he talks, the way he looks crazy, Have you seen him? You have seen him, right? Anyway, so we don't want that in the human history again that happened. But unfortunately, right, some countries are keep supplying their technology of this bomb to some other countries, right? That's another dangerous thing because. Anyway, so let's go back to spectrum of the gamma ray. We talked about that X-ray. X-ray is dangerous too, right? It is dangerous. If you go to the X-ray machine, I know many of you have experience with the X-ray for some reason, medical purpose, right? When you go there, they cover you by the lead, right? Why? Because it's dangerous. It kills, affects the DNA. It ended up gets cancer. And you know that the people who work for the atom bomb throughout the world, they ended up, most of them, I cannot say all of them, most of them died out of cancer, even in US. The people who work in the Los Alamos, New Mexico lab, Washington project for discovering atom bomb in this country, like maybe how many years ago? 60 years back, right? About. Because each generation is 30, 35 years. So 2 generations, about 60, 70 years, okay? And those people, most of the scientists was died of cancer. Okay? So X-ray, gamma ray, yeah, Mohammed. Sir.
I have a question, but what about the person who is really having an X-ray? So the rays can affect that person too.
Who was working with the X-ray?
Yeah, who is having an X-ray? Because they, like if you go with someone who is having an X-ray, they move you to other room. They're like, don't want to stand over here, but what about the person who is having an X-ray? So.
You mean who is doing X-ray?
No, like, if I'm going for an X-ray, so that rays can affect me too. But if there's someone going in with me, they will move him out.
Yeah. There's sometimes, that's why they say nobody else allowed in the X-ray.
Yeah.
So, and of course there is chance. So better not to have X-ray as much as possible, And just can be, because we need it. We need to do X-ray, right, sometimes. So I usually don't go X-ray until, I usually never go until I can remember when I was younger, I used to do, So try not to do that. And yeah, there is a chance it can mutate our DNA, yes. So the more dangerous is the food one, right? Fungus, mold, right? That's the more dangerous thing to get cancer than this stuff, okay? Because X-ray we barely do that. and we are protected by lead shield when you go to X-ray machine. So more dangerous things for cancer, you should be careful with the mold. Nowadays, after the Herbie, a lot of people got affected with the mold, and those houses are dangerous because mold grow in our body, and when you eat sugar, they multiplies. So make sure you should be aware of the mold, and then the chemicals, preservatives, right? And UV also can make a cancer in our skin. So even though sunlight is important for our body, but it should not be stay that long, whole day burning because of the vitamin D. Remember that. It can make skin cancer when you have long time. Keep burning yourself, hey, vitamin D, be healthy. Yes, it is healthy. Yes, if you burn your belly, it's good for your liver and clean our body, It is important, yes, sometimes we should do that, but not because keep doing every day, burn and then get cancer, okay? So that's the UV. And visible, the tiny part, tiny range of wavelength is visible, right? And then IR for warm up the food, and microwave also warm up the food, another way of microwave and IR. And IR is not warming the food, IR can keep your food warm, right? For the light, some store they keep food warm by a red light. That's you need. But when you go microwaves are easy dangerous. Not that level, but for the microwave, what things to be careful is microwaves only work with the water. If you have something dry, if you put in microwave for a whole day, 10 hours, it's not gonna heat up until they have some water molecule in it. So the way microwave work, it vibrate water molecule and makes temperature high. Okay, that's how food get warms, because food is always have some water in it. And then FM and AM. AM have highest wavelength, but FM has higher energy. So we prefer FM than AM, right? Okay, let's go to the famous equation, wavelength and frequency. So frequency equal to C over wavelength. So wavelength equal to C over frequency. So frequency equal to C over wavelength. So this could be applied to calculate as needed. For example, this one. If I have a frequency this, what is the wavelength of blue light? So wavelength equal to C over frequency. So C is always constant, 10 to 8 meter per second, and frequency is 6.4 times 10 to 14 per second. So if that happen, the unit cancel out, per second cancel out, you can get lambda in meter. What happened? One thing you need to be careful. In this chapter, problems are very easy. When you solve it, people sometimes forget about units. I'll show you the next problem. So this problem you have, you plug in the value C and nu, you can get the value of wavelength after cancelling out second and per second, and then meter is going to be, so 4.7 times 10 to negative 7 meter. That's the wavelength. Look at here. What if you need frequency and you have a wavelength? Can you solve it? Yes, do that. So one thing just need to be careful, people forget, is wavelength in nanometer. That need to be in meter. You convert that first before plugging in here. So you're gonna be, yes. So calculate frequency equal to C over lambda. Make sure transfer it to meters. Okay, nanometer is 9, so
10 to the negative 9? Yes. Isn't it 10 to the negative 9?
yes,
10 to the negative 9.
10 to negative 9, yes. You know how to do that, right? Take your time to do that.
You basically just rewrite it.
You can erase the wave.
Oh, like,
You can erase that one, yes.
if you did remember, some of them don't.
So regarding the negative value, so if you make it 6.81, that would be 7, right?
Okay.
That would be 7.
So it's 7.
Oh, no, 7, yeah, okay, 7. This is going to be 6.81 inches.
I moved it, that's going to help throughout, so you have
You look at one. So when you make it nanometer meter and move the decimal, the 9 going to be 7.
Okay.
It's 10% to the negative.
Yeah, do that.
Wait, why is it negative 7?
Did you guys remove the decimal point?
Because you're moving the decimal. So decimal was after 11, right? There's no decimal here. So you're moving decimal 2 digit. So it was 9, now it's going to be 7.
Yeah, that's what I got.
We forgot to put negative. Did you put negative?
Yes.
No. No. Actually, the other way. Because 1.
Oh,
Smaller and we are bigger.
Times 10. Times 14.
I called him because he's doing always UM exam. Question. He's doing the UM exam. So he comes to class, he's very quiet.
Oh, yeah.
So I just said, okay, come on. Then, so do you got the same value? So per second, another way of expression is hertz. So you can put hertz instead of per second, okay? And you should know the both units. So this is another one, which is green light, and you have a wavelength. What is the frequency, right? If you have a wavelength,
That's the.
you can get the frequency, right? Same. Okay? Similarly, you have a nanometer, you have to convert it to the meter first. You see? Nanometer, convert to the meter first. And then get the unit in hertz or per second. Then we'll go to the new part of this chapter. This section is talking about the photoelectric effect. What is photoelectric effect?
The rejection of the
Interaction of?
Emission of electrons from metal surfaces.
Exactly. This is emission of electron from a metal surface by what? By metal? Go ahead. Okay, when you pass light, when you pass a beam of light on a surface of metal, then what happened? The photon means the unit of energy of light you radiating in a metal surface. So metal surface have electron, metallic bond, metal have a sea of electron. This electron and photon of light, energy of light, get a collision. So radiation comes, make a collision between electron and photon, not proton, right? Photon is called a unit of energy of light. So light falls in a metal surface, so photon of light and electron have a fight, have a collision. Then, so metal surface makes electron that irradiate from the metal surface. That's called electromagnetic effect. So that in short, light falls in, get a collision with electron, and then electron comes out. That's called electromagnetic effect. So light have two properties. Light have a wave property, light have a particle property. So this kind of wave particle property of a light falls in, is it gets excited and comes out. Electron comes out. So like a metal surface, okay, then this is a photon and then electron comes out. That's called electromagnetic effect. So initially Planck was discovering before Einstein. Einstein, all of you know him, this fellow scientist, he discovered this photoelectric effect in 1955. And because of that, he got a Nobel Prize to discovering that. You see how it works? So the photoelectric effect and electron, emitting electron, when it gets shined by light. So this electron emission does not depend on that high intensity light will make high emission of vector. It's not like that. So if you have a specific wavelength of the light of energy comes in, then it irradiates, it makes emission of energy as an electron. That's called photoelectric effect. So for instance, if you have a beam light, look at that, it's a dim light of blue. It is able to make an emission of electron. But even though you have a red light, it's not possible because it is a specific wavelength of energy which is possible by blue light, not the red light. So it's not about the intensity. Even the dim light, it makes electron emission because it is specific wavelength, but red light is not possible even though it's high intensity. This is another example how electron emission forms. So how you calculate the energy? So we'll be learning how to calculate this photon energy. Its energy depending on this energy depending on Planck constant, which is h and nu. So the energy of the photon is depending on the energy, depending on the Planck constants and frequency. Remember I said blue light is possible to make emission because blue light because it depends depending on the frequency. So the frequency is needed to calculate the energy, and Planck constant H, which is constant value, which is this value, 6.626 times 10 to negative 34 joule second. So let's see how we can calculate the energy. If you have a wavelength 486, and then what is the energy? Can you calculate that? So if you have a wavelength, but I don't have a wavelength in here, what you can do, I have a H, and as you know previously that frequency equal to C over lambda. So put C over lambda, you see? And wavelength is given, so energy equal to H, put the H value, and C is the speed of light, and lambda is given. Please calculate that. So H value is constant 6.63. So 6.63 times 10 to negative 34 joule second over 3.00 times 10 to 8 meters per second and over lambda. So lambda is 4.86 times 10 to negative 7 meter. Calculate that. So here you cancel out second and meter. So you're getting energy in a joule. If you calculate that, you will have 4.09 times 10 to that is second meter. Joule.
So the constant is joules per second.
So constant joule second, not joule per second, joule second. Because if it is joule per second, then you can cancel out because yes, top and bottom.